Buggers of the world. Come here, buggers of the world. What? Oh, thank you for the num-nums. Thank you for those num-nums, sweet boy. Hey, bugger. How do you feel about Nicholas? How do you feel about Nicholas? Hmm? You happy now? Okay, we have crossed the 20 viewer threshold, so that means I'm going to start. Hello, everyone. Happy Friday. I think I changed the title of the stream, did I not? It is period 6. I just forgot to change the title in between classes. So I'll change it in post-production. So I'm going to talk a little bit about last time's lesson, which is was a pretty significant lesson. So last time we learned Newton's law of universal gravitation, which gave us an equation for the gravitational field. And the equation was big G times big M over R squared. Okay, so let's talk about what each of these things means. Little g is the gravitational field. But the gravitational field is just a synonym for the acceleration due to gravity. Okay? It's the same thing. There's a question in the chat. When will I be putting grades into Q? Not in the next week. I'm finishing up this class and I'm going on vacation. Okay? If you dump a bunch of work on me the day before vacation, then there's no way in heck I'm going to grade that stuff over the vacation. All right? I'll handle it when I get back. M is the mass of the thing making the gravitational field. And this really depends on perspective. So if I wanted to calculate what is the gravitational field that I experience due to the Earth, then the thing creating the gravitational field is the Earth. But if I wanted to calculate what is the gravitational field that the Earth experiences due to me, then I would be big M. Okay? R is the distance from the center of the mass to the location where you want to calculate gravity. Okay. So yeah, if you're at an altitude, so like right now we're on the surface of the Earth, but we wouldn't use r equals 0. We would use our distance to the center of the Earth. Okay. If you're at an altitude, so like let's say that you are up above the surface of a planet, and this distance right here is r1, but then the radius of the planet is r2, then you would use big R equals r1 plus r2. Okay? Bug, why are you so playful today? Huh? Bug and Hazel are having battles all morning. I just love it when two dogs are like facing each other and they're really tense, and it's like their ears are sideways. So this is what my dogs do. They put their heads right up against each other and both their ears are sideways, and then they both go like this at the same time. They both go. It's really funny. So big G is a constant of nature. It's the same in every single problem. It is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay? So that was the main equation we learned. We also learned an equation for the gravitational force, which we already knew this equation because it's the same thing as the weight force. And it's little m times g. So, of course, little m is the mass of the thing experiencing the gravitational field. Okay? So that's what we did last time. So I just wanted to review it because it was pretty significant. So what we're going to talk about today is the circular orbit. And that's important, circular orbit, because not every orbit is circular. So I'll come to that, back to that at the end of the lesson. But the circular orbit of a satellite about a central body. Okay? So that's the topic of today's lesson. So let me draw a picture of what that would look like. You have a central body. With mass big M. Okay. And then you have a satellite that is in a circular orbit. The satellite has mass little m. So the satellite is going in an orbit around the central body. The distance between the center of the central body and the edge of the orbit is big R. Okay? So one important point about the case that we are going to consider is that the mass of the central body is much greater than the mass of the satellite. So this, if you put 2 greater than signs, it means much greater, okay? That's a symbol that's used in math sometimes. So why is it important that we have the mass of the central body much greater than the mass of the satellite? Well, if you have 2 things orbiting that are of equal masses or nearly equal masses, we have something that looks like this. They dance around each other. Okay? They dance around each other. So, for example, did you know that out of all the star systems in the universe, most of them are binary star systems, meaning that there are 2 suns? So it's actually more common to have 2 suns than it is to have 1 sun in a star system. Okay, and suns will typically have approximately the same mass. So when they orbit, the 2 stars are orbiting each other like this. Okay, but by having the central body much more massive than the satellite, the central body basically stays put while the satellite goes around it. You see what I'm saying? So basically, the more unequal the masses are, that central body will stay more in the center. Okay. So that's why we have that. So the sun is much more massive than each of the planets, and so the sun basically stays put while a planet moves around it. The moon is much less massive than the Earth, so the Earth basically stays put while the moon goes around it. Okay. A couple of years ago, we had a probe that flew by Pluto, and Pluto has a moon called Charon, Charon, and Pluto and Charon are approximately the same mass. So as the probe was approaching Pluto, the probe was taking pictures of Pluto on approach, and because the Pluto and its moon have approximately the same mass, they were actually orbiting around each other. So you can actually look up the video of the approach to Pluto, and you can see them orbiting around each other. It's kind of cool. Fun fact, the closest star system to the sun is called the Centauri system, and it is not a binary star system, it is a trinary star system. So the Centauri system has 3 stars, and it has 2 heavy ones that are orbiting each other in the middle, and then a third smaller star that is orbiting the 2 of them from the outside. So it's a pretty different star system from what we have here, because our system only has 1 star and they have 3 stars. Okay. So what we're going to do is we are going to do Newton's second law for the satellite. Okay? So Newton's second law is net force equals ma. All right? Now, because it's Newton's second law for the satellite, the mass on the right-hand side is the mass of the satellite. Okay? If we were doing Newton's second law for the central body, we would use this mass. Okay? Now, the satellite is moving in a circle, so there has to be a centripetal force. So that centripetal force is the gravitational force. Okay? Because this is the gravitational force right here, where m is the mass of the thing experiencing the gravitational field. So this would be the mass of the satellite. So notice how we have mass of the satellite on both sides of the equation. So it cancels out. Okay? Going to the next line, on the right-hand side, because the satellite is moving in a circle, I'm going to use the formula for centripetal acceleration. And I gave you two formulas for centripetal acceleration. One was v squared over r. We're going to use the other one first. Okay, we'll actually use them both, but first I'm going to use the second one, which is 4 pi squared r over period squared. Okay, and then on the right-hand side, we have gravitational field that the central body creates, which is big G times big M over r squared. Okay, so now what we do is we're going to cross multiply. Okay, so on the left-hand side, we have G big M t squared. Okay, and on the right-hand side, we have 4 pi squared, and we've multiplied this r squared by the r that's already on the right-hand side, so we get r cubed. So this is our main result for today, and it is called Kepler's second law. And towards the end of this lesson, I will talk about who Kepler was. All right. So this is actually a really, really, really nifty formula. Okay. It has 3 variables in it. The 3 variables are mass of the central body. Okay. Period of the orbit. Period of satellite orbit. And it has the radius of the orbit. Okay. So if you know 2 of these variables, you can solve for the third one. Okay. So for example, what if we knew the mass of the central body and we knew the radius of the orbit? We could predict the orbital period. So we could actually predict the time it takes for a satellite to go around. If you knew the mass of the orbit and you know the period of the orbit, you could figure out what the radius of the orbit is. So this is used by NASA. The equation is used by NASA in this form because if you want to put a satellite in orbit about the Earth with a certain period, this equation would tell you what does the size of the orbit need to be. So it tells you, how much fuel you need to carry in your rocket to get it that far away from the Earth. Okay. But the third thing I think is the coolest application of Newton's second law, Kepler's second law, excuse me, is if you know the period of the orbit and you know the radius of the orbit, and this is actually pretty easy to determine because how could we determine the period of a satellite's orbit? Well, we look at it through a telescope and we literally watch the thing go around and we time, you have a watch, you go, look at your watch, and then you look at the satellite and you can figure out how. I just know that's going to be the thumbnail that's probably going to be the thumbnail for this video. It's going to be, watch. I always wonder, how does Google figure out the thumbnails? And I think somehow they have some AI that detects like big motion or weird facial expressions. So you're looking through. Now I actually want it to be this. You're looking through a telescope. You time the period of the orbit, And you can also see the size of the orbit. So you use a telescope to figure out what is the period and the size of the orbit, and then you can calculate the mass of the central body. Okay? So think about that. This is how we know what the mass of the sun is. Okay? We can't pick up the sun and put it on a scale. So how do we know what the mass of the sun is? Well, what we do is we look at the satellites of the sun, which are the planets. We determine the size of their orbits and the period of their orbits, and we use Kepler's law to determine the mass. Okay? How do we know the Earth's mass? We look at the satellite of the Earth, the moon. We look at the radius of the moon's orbit. We look at the period of the moon's orbit, and then we can determine the mass. Okay? So, so this is how we determine the mass of the central body. Now, what if we wanted to determine the mass of a moon which doesn't have a satellite? In that case, there are other methods, but they're a lot less accurate. Okay? So basically, what I wanted to say is we use the orbital parameters, or I should say the orbital properties of the satellite to determine the mass of the central body. Okay? One thing that's really interesting is this is actually how we've determined the existence of black holes. Okay? So if we look to the center of our galaxy, there's a region where stars, not planets, but stars are orbiting a region of space. So the stars are the satellite, okay? We look at the radius of the star's orbit, we look at the period of the star's orbit, and we determine the mass of the central body, okay? Then, what astronomers did is they looked in the center to find the central body, and guess what they saw? They saw absolutely nothing, because it is a black hole. Okay? So what we were able to determine is that there is an incredibly massive thing in the center of our galaxy that is invisible. And so the only thing that fits the bill is a black hole. Okay? Another thing I wanted to talk about is what if the sun were to be compressed into a black hole? So we don't change the sun's mass, but we change its size. We compress it a huge amount, and when we compress it a huge amount, it turns into a black hole. Okay? What would that do to the orbit of the Earth? And the answer is it would do absolutely nothing, because the properties of the orbit only depend on the mass of the central body. It doesn't depend on the type of central body. It doesn't matter whether the central body is a star or a rock or a black hole or a blob of water. It doesn't matter. The only thing that matters is the mass of that central body. And then as long as the mass of the central body is the same, the Earth can go in its same orbit. Now, what would be catastrophic would be the fact that if the sun became a black hole, it would no longer be emitting light. And so the Earth's surface would get very cold, and life would probably not be able to survive in the way that it does today. I actually think bacterial life would survive from the heat of the Earth itself. All right, so, and then one more thing before I flip the page, which is, notice how the mass of the satellite canceled out. So what that means is that the period of the orbit does not depend on the mass of the satellite. Okay? So if you have two satellites, okay, so let's say you have satellite A and satellite B, and they could have vastly different masses, okay? But if you put them into the same circular orbit, they're going to maintain their distance between each other because they're going to go in an orbit with the exact same period. One won't orbit faster than the other, okay? So that's important. What would be different is the heavier a satellite is, the more energy you need to get it into that orbit in the first place. So a light satellite is easier to put into orbit. It takes less fuel to put it into orbit than it takes to put a heavy satellite into orbit. Okay. Interesting fact. I believe it costs about $10,000 per kilogram that you want to put into orbit about the Earth. So if you're 50 kilograms, it would cost about $500,000 to put you into orbit in terms of, with the current technology. So that's why not a lot of stuff goes into orbit. All right, so let's flip the page here. And let's do an example. The sun has mass 2 times 10 to the 30th kilograms. Okay, how do we know that? We know that by observing the satellites of the sun. Neptune, the planet Neptune, orbits 30 astronomical units and I'll explain what an astronomical unit is in a moment, away from the sun. Calculate the period of Neptune's orbit in Earth years. Okay. So, first of all, what is an astronomical unit? So an astronomical unit is typically abbreviated by AU. So I from now on, if I ever bring it up again, which I don't know if I will, but I'll just say AU, okay? Now, 1 AU is equal to the sun to Earth distance, okay? So by saying that Neptune orbits 30 AU away from the sun, it's saying that Neptune is 30 times as far away from the sun as the Earth is, as we are, okay? So what is the value of an astronomical unit? It's 1.5 times 10 to the 11th meters. Okay? So we're going to use Kepler's second law. G m t squared equals 4 pi squared r cubed. Okay? Let's plug in numbers. G, 6.7 times 10 to the negative 11. M is 2 times 10 to the 30th. Now remember, M is the mass of the central body. It's not the mass of Neptune. It's the mass of the central body times period squared equals 4 pi squared r cubed. Now for r, I can't just put in 30 because it's 30. I have to, this r is in meters, okay? So I have to convert 30 astronomical units into meters. So 30 times 1.5 times 10 to the 11th, and that number cubed. So what I would recommend you do in this case is multiply out the numbers on the left-hand side, multiply out the numbers on the right-hand side. So just take it slow. You'll end up saving yourself time by taking it slow with scientific notation numbers, because it's really easy to type it in the calculator the wrong way. So multiplying these two numbers together, and I get 1.34 times 10 to the 20th times period squared. Doing it. Now when you cube this scientific notation number, you want to put the entire thing in parentheses. Oh, this should be 4 pi squared, my bad. And I get 3.6 times 10 to the 39th power. So this is why you ever hear someone say, oh, it's so huge, it's astronomical. This is why they say that, is because when you're dealing with astronomy, you tend to have really large powers of 10. Okay. So now what I'm going to do is I'm going to divide. And when you're dividing scientific notation numbers, you want to make sure to put both the numerator and the denominator in parentheses. Okay, otherwise you will get the wrong answer. So what we get is period squared equals 2.7 times 10 to 0.7 times 10 to the 19th. And then this is t squared, so I have to take the square root. Again, taking the square root, I'm going to put the entire scientific notation number in parentheses. Okay. And I get the period is 5.2 times 10 to the 9th. Now this is all in SI units, System International Units. So this equation is going to spit out the time in seconds. But I didn't, so 5.2 billion seconds. But I didn't ask for the answer in how did I get the 3 there? Because Kepler's law is r cubed. So this cube, that's where it comes from. So we want to convert this to Earth years. So I'm going to use the fact that 1 Earth year is 3.15 times 10 to the 7th seconds. Okay, so you can figure that out by just doing 365 times 24 times 60 times 60. Okay, so it's 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So 3.15 times 10 to the 7th seconds is 1 year. So we got to divide these two numbers, and I'm just doing the unit conversion that you are familiar with from your other classes, probably chemistry. And I get about 165 years. Earth years. Now, the period of Neptune's orbit is also 1 Neptune year, but we put it in Earth years. So what does that mean? It means for every 1 orbit that Neptune does around the sun, the Earth does 165 orbits. Okay, which is really funny to me. So if we could sort of play the video of the Earth's of the solar system and make it go fast forward, you would see the Earth just going while Neptune's coming around the outside really slowly. Like that, okay? Which I think is fascinating. If we did the same calculation for Pluto, we get something like 250 years or something. It's hilarious to me because since Pluto has been discovered, it has not even completed a full orbit around the sun yet. Okay. One thing I wanted to talk about is let's say that you wanted to solve for the radius of an orbit. Okay. See how we have r cubed? Okay. So if you try to solve for the radius with Kepler's second law, you're going to end up with an equation that's like r cubed equals a number. So I just want to briefly remind you how to solve for r in this case. You would take the cube root, which is equivalent to raising to the 1/3 power. So if you solve this, you raise both sides to the 1/3 power, and you would get r equals number to the 1/3. Okay, so I just wanted to make sure everyone was on the same page with that. Because I know you take square roots all the time, but I don't know how often you need to take cube roots. But this is one of those times. All right. So let's talk about the speed of a circular orbit. All right. So Kepler's law allows us to calculate the period, but not the speed. So let's calculate the speed. And so what we're going to do is if you go through my calculation again, we canceled out mass of the satellite from both sides, and we had gravitational field equals acceleration. And then I use the equation 4 pi squared r over period squared for centripetal acceleration. But what if I use the v squared over r equation? Okay. And then the gravitational field is still g times big M over r squared. So now I can take this equation and I can solve for speed. Okay. And so you multiply the r over. It cancels out one of the factors of r in the denominator on the left-hand side, and then we take the square root. So what we get is that the speed of a circular orbit is square root of g times big M over r. Okay. So this is kind of our second result for today. And when you calculate that for a typical star that has a planet that's a typical distance away, what you will find is that planets are typically orbiting with speeds of the order kilometers per second. Okay? So planets are orbiting quite fast. Now, let's talk about how does this depend on mass? Well, the more massive the star is, see how M is in the numerator here. The more massive the star is, the faster the things that are orbiting are going. Okay? And then we can see R is in the denominator, so the bigger the orbit is, the slower the speed of the orbit. So this explains why Neptune's orbital period is so much more than Earth's. Okay? The reason is that Neptune is way farther away. For one, Neptune is way farther away, so its speed is less. And furthermore, because it's way farther away, the size of the circle that it's traveling in is much bigger. Okay? So there are two things that are making Neptune take so much longer to go around the sun. It's because it's going slower and it has further to travel. Okay? So the last topic for today, you might have noticed that I called this Kepler's second law. So what are the other laws? All right. So I want to talk about that briefly. And who was Kepler? Okay. So Kepler was an astronomer, and he collected very detailed information about the orbits of all the planets that were known at the time. Okay. I can't remember which planets were known at the time, but I know, Venus, Jupiter, Mars, and probably Saturn were major parts of him developing his laws. Okay, so his first law says that orbits are ellipses with the sun at one focus. So what is an ellipse? An ellipse is basically an oval. So if we were to look at a top view, if we were to look at the top view of an orbit, it's going to look like an oval, so an ellipse, something like that. Okay, and an ellipse, if you remember from your math class, has two foci, which are kind of like right here and here, maybe. Okay, and the sun is at one of the foci. So the sun is actually not at the center of the Earth's orbit. It's actually offset. Okay, and then there's nothing at the other focus. Just empty space. So now the thing is this: there are lots of different ovals we can draw. We could draw an oval that looks like this. We could draw an oval that is like super elongated, or we could even draw a circle. A circle is an ellipse. It's just an ellipse that, has this direction equal to that direction. Okay, so the more flattened the oval is, the higher the eccentricity. There's a word in astrophysics, it's called eccentricity. And the bigger the eccentricity is, the more ovally the orbit is. Okay? Now it turns out we analyzed circular orbits. Now, why did we analyze circular orbits? Well, because the eccentricity of the planet's orbits are very small. So they are approximately circles. Okay? So this is a not eccentric orbit. This is an eccentric orbit. So the planets have orbits that are not very eccentric at all. So they are ovals, but they're ovals that are very close to being circles. Okay? And it's good enough for our purposes. Now, if you want to analyze an elliptical orbit, the math gets significantly more complex, and it doesn't really enhance the understanding all that much. So that's why we don't talk about the general case of elliptical orbits. Okay? but all the planets have orbits that are slightly eccentric. So there are astronomical bodies that have orbits that are highly eccentric, which are comets. Okay, comets have orbits that look like this. This explains, and by the way, the more eccentric the orbit is, the more the focus gets shoved to the left-hand side. So, the sun is right here. You might have heard of a comet called Halley's Comet. Halley's Comet is a comet that comes by about every 80 years. And it's in a very eccentric orbit. Comets tend to have eccentric orbits. And when the comet is out here, far away from the sun, we can't see it for two reasons. One, because it's far away, and two, because when it's far away, the surface of the comet freezes, and so that giant cloud that we see is gone. Okay, it's all frozen onto the surface of the comet. But when the comet is here close to the sun, it's closer to us, so it's easier to see, and the surface melts because it's close to the sun now, and the melted surface then sublimates, or I think it just directly sublimates. So you have all this water on the surface of the comet. It sublimates into this giant cloud of water vapor that surrounds the comet in the center, and the light from the sun reflects off of this giant cloud. So that's why we can see the comet more easily when it is in this part of the orbit. Okay. Kepler also has a third law, which says that planets orbit faster when closer to the sun. Okay? Same thing with comets and everything. So this is particularly true for comets. So when a comet is out here far away from the sun, it's going very slowly. And then as it gets closer and closer to the sun, it starts to go faster and faster and goes wing, slow, wing, slow, wing, slow. All right? So that's what the third law says. All right. That is my lesson for today. So I will see you in the Zoom room for